first is a definition problem. So XD is called a metric space if there exists a metric D defined on X, such that for all x, y, in X, the distance are larger than 0 and equals 0 if and only X is equal to Y. And the symmetry condition and the triangle inequality dxd plus ddy is larger than dxy. So that's the first question. So the second question is to ask you whether this D defines a metric on positive zero numbers and 0. So is this correct? So if this correct, it will be really strange. So you may guess that it might be wrong. But the first condition and the second condition are trivial, correct? So the problem is where the third, yeah, it's trivial, right? Because it will be larger than 0 and x, this is 0 if and only if x equals to 1. So the problem is the third condition. Is this hold? So the simplest solution to this problem might be that x equals to 9, y equals to 1, z equals to 4. So d dxz plus d dy is equal to 2, 1 plus 1, and is smaller than dxy. So that's the one-line solution, because it gives a counterexample for the third condition. So D did not define the metric on X. But what if you don't want to do like guessing wrong numbers? Okay, we can check the conditions. So when this inequality does not hold, that is dxy will larger than dxd plus ddy. So let's write down. So minus dxy. This will equal to square plus d minus d square y square x square y. So we expand this. The x and the y term will cancel out. So it remains minus 2 square. And there's 2z and a root xy. So this will equal to this will equal to this. So when will this is larger than 0? So it will imply that z is larger than both x and y, or z is smaller than x and y. Sorry. So when z is larger than x but smaller than y, this term will smaller than 0. So that's why this one will give a counterexample, because x is larger than z and larger than y. Also, this is a contradiction, because this does not hold for any xyz in x. Any questions? Third one, set of irrational numbers. So what are irrational numbers? Irrational numbers are real numbers that are not rational, right? So it is equal to the set R minus Q. So since R is uncountable and Q is countable, so it is a set of uncountable. It is an uncountable set minus a countable set. So this will be countable. So this implies that it's uncountable. Okay. Second one. The second one is the set of the sequence. So is this set countable? This is look like the binary expression of real numbers between 0 and 1, because for the numbers in 0 and 1, you can write like 1 over 2 is equal to 0.1, 0, 0, 0, or 1 over 3 is 0.0101, and something like this.
Do you know the binary representation?
No. No. Oh, so this means that plus 0 plus 0, and this means that 1 over 4 plus so in this if this has 1, this is 1, this means that 1 is if this
the digit there means the nth digit after the W is representing 1 over 2 to the n. It's like when you do, we usually do things like this. Like, that's the usual one. We mean A1 over 10 plus A2 over 10 squared plus A3 over 10 squared. But now, what I want to say is we change it like this one. So we can represent things in this kind of representation, binary representation.
So you know that the numbers between 0 and 1 are real numbers between 0 and 1 are uncountable. So this set is uncountable. So how can you prove it? Is that we prove by contradiction that so you know that suppose.
I think if they do not know the binary representation, you should work on it with the diagonal.
Yes. I just given intuition that this set is uncountable. Suppose S is countable. What we mean S is countable is that there exists a function f such that f it defines a bijection between natural numbers and S. This symbol means bijection. So we have f1 equals x11, x12. So using the diagonal method, we can choose that the first element is different from x11, and the second element is different from x22. So keep going, we construct a sequence. if we construct y like this, we will have y is still the member of S, but there's no n natural number n such that Fn is equal to y by our construction. So this gives us a contradiction. So we have that S must be uncountable. Any questions? Yes, it's using a counter diagonal process. And the fourth problem is a metric space. So we first have that dxy is equal to the root of so we need to check the three conditions. So for all xy Rn, dxy it is here, so it is larger than 0. It is larger than 0, right? So and dxy equals 0 if and only if every xi and yi are equal. So which means that x is equal to y. Okay. The symmetry condition is trivial as well because you just okay, I don't write this. The third condition is to prove dxz plus dzy is larger than dxy. So we first write the left-hand side, which is equal to so because with root we can do anything, so we add a square here. Because we know that this part is larger than 0 and this part is larger than 0 as well, so we can just prove their square. This square is larger than dxy squared. Okay, as we say in the previous course, this looks like Cauchy. So I explain later if you don't observe to use Cauchy here. So this will equal to larger than equal to So what if you start here? So if you start here, if you start on the one side, you can go to another side to see what can you do. So the right hand side is equal to some xi minus y squared. So suppose that we are at here. So how can we make these two equations more similar? We have to generate this term, which is so this will equal to So now look at this one. You only need to prove that this is larger than this. So you only need to prove this term is larger than this term. So this is actually Cauchy. So if you don't, if you stop at this, it is okay. You can go to another side and keep going.
So right hand side squared, right?
Yes. Oh, yes, it's square. Any questions? Okay, last questions. The questions is to count polynomials with integral coefficients. So how can we count the number of polynomials? We can count it by degree. So if the degree is 0, we have the polynomials like 0, 1, 2, minus 1, minus 2, because it only has the constant term. And if it is degree 1, we have x plus 1, x minus 3, like this. So you may want to write Pn as polynomials in P, and the degree P is n. So doing this, you can write P is the union of Pn. This means that natural numbers at 0. So recall that the countable union of countable sets is countable. So if we can prove that Pn is countable, then we are done. So how can we count the polynomials with degree n? So say the polynomial is xn plus a0. What determines a n degree polynomial?
The 0 should be on the
Oh. It is a coefficient, right? So you can map to a n plus 1 tuple in D n plus 1. because if we have a polynomial, we can have a n+1 tuple like this. And if we have this tuple, we can write it back and get a polynomial. But is Pn and Zn+1 completely the same? No, because in Pn we have a restriction that An cannot be 0. So that's bad. So how can we deal with this problem? Is to add the inequality here. So in this way we can, so this restriction go disappear, and we can make a projection here. So we claim that Pn is isometric to Zn+1.
I think they use similarity.
Similarity or
isometric. I think it's similar. I remember that they use similar but not isometric.
okay, similar.
So it could be one tilt, but not this one.
Okay. So we can find a bijection by so this defines a bijection. So we have Pn is similar to Zn+1. So by our claim, P is equals to Pn and is similar to the union of Zn+1. Okay, so now we know that this Zn+1 is countable set, and N0 this is a countable set as well. So it is a countable union of countable sets, and hence countable. So the last thing we need to do is to prove the set of algebraic numbers are countable. So the algebraic numbers is the real numbers, the numbers that is the root for some integral polynomials, which is the union of all polynomials roots. So from previous discussion, P is a countable set, and the root of P is at most degree P. So this is which is countable. So again, this is a countable union of countable sets. It's countable.
Countable union of at most countable sets.
Yes. Okay. Finite set. Okay. Finite sets.
Finite sets.
Okay. Finite sets. So it is countable. So
So it is at most countable, but we know that it's infinite, so it should be countable.
the key point is to observe the bijection between the polynomials and the n+1 tuple. So I give an
Okay, so
give me 3 minutes.
Okay.
So before ending this question, I give an example, a comparison to So can we write real numbers in A in this way? Can we do something like this, just like how we do here? We know that this set real numbers are uncountable, but here is a countable union of finite sets, so this term must be countable. So what's wrong? Can somebody tell me? Anyone?
Can you explain again what A1 is?
A1 is like 0.1, 0.2, 0.3, like this, something like this. And A2 will be 0.1, 1, 0.12, something like this.
So n means like you have n digits.
Anyone? Okay, so the problem is that in this set it does not contain 1/3 equals 0.3333. Because by definition, if any element in this set must be in one of the AN, this means that its digits must be finite. So 1/3 is not in here, but in here. So although this is the infinite union, it does not mean that it will contain rationals like have infinite digits like this. So in same as this case, same in this case, because it doesn't contain like the power series like this. This element is not in P. So that's why P is countable. If it contains power series like this, then it will be uncountable. So the finite degree here is important. Is that clear? Okay.
Now I'm gonna show like 2 ways when we like deal with the countable and uncountable things. Like 2 common tricks. A is countable, B is countable. A, B equals to A. Intuitively, you plus small little things after a big thing, so it does not change anything. The proof will be. So this is a small trick. When we want to do this kind of thing, we usually do things separately. So we want to construct. I'll just show you. Okay, take some C in A that is countable.
What does it mean to the value of the number of elements of an
There exists a bijection. What I mean is, hijack F. That's what how we count things. Cool. We see A, and then we combine F1 is from A minus C to A minus C. That is adjective. And this one is also adjective. Because this one is countable. Countable union countable is countable. And this one's countable. So you combine these two, then you can get the whole set. So it's like this one. This one's A, here's B. And here's only A. What you do is to remove a countable part here and to remove a countable part here. And you say that, okay, so this part to this part. And these part so consider combine F1 and F2 to F, and F is adjective. Alright. So you can do a practice at home that consider practice for this trick. A is a countable. B is countable, and then a subset of A. Try to prove that proof equals to A. Which is the same trick. Alright, consider this kind of question. And a second trick is to construct a function from it to another countable set. So the proposition will be, okay, let's say S contains this joint, open intervals. Then S is at most countable. Do you know what do I mean by this proposition? So I consider this one's R, and S would be like, okay, I have several open intervals. So as like do this, so the element of S would be this one, this one, this one, and this one. So S would look like A1, B1, A2, B2, something like this. And there's at most countable.
Before we go on, so
I'm confused about the combine. Combine F1 and F2 and then to what?
To F. So you would write like F as equals to F1 of X, F2 of X. If X in A minus C, if X in B of C.
I see, okay.
So do you understand it now for this figure? So we're considering like disjoint open intervals on R. They're at most countable intervals. The reason is every interval contains a rational. And because of this joint, you can see that there's no two open sets contain the same rational. Right? So on this, you have constructed send S in S to some R in S, R in Q. By this function, you can see that
Wait, sorry, when you say S is most countable,
it may be finite or countable.
I know, but I mean, it's countable in terms of intervals.
Yeah, the number of intervals.
I see, okay.
The number of intervals.
Yeah, because.
So you send.
Yeah, because taking out.
One interval is countable.
Yeah.
So if you send this one to maybe let's say R here, R1 here, R2 here, so it's just doing this kind of pairing, right? So you see that S is at most the number of Q. So it is at most countable. Okay? I know it's like magic, it is magic, like I'm not going to deny it.
And why would we want to consider infinite disjoint open interval?
You'll see in the following practice, okay? Practice.
Did you make this up for fun?
It's not me, it's like Cantor or Weierstrass, they do this for fun.
I mean, if you want to talk about fractals, then you will have this, right?
Practices. One is F is from R to R. Let's say it's monotone. Do you know what monotone means? Like increasing or decreasing. Prove that you have a 10 calculus right, so you know what is discontinuity. Prove that again. They are at most countable discontinuities. And the second consider E is a set of eights that on R2 that do not overlap each other. So thinking about like E is a set like you're doing this keep drawing 8. And they do not overlap. So the line of 8 do not overlap. They cannot do this. They overlap here. Okay, so they do not overlap. They do something like this. E is at most couple. So the trick here is you need to find out, okay, so how to map the discontinuity to something countable set you know. Or how to map those 8 to some countable set you know. Right, that's the trick here. And you need to like take some time to figure it out. It will not take, maybe we'll take some of the practice into our exam, but yeah, I'm still thinking about it. Just try it, and if you cannot figure it out, you can discuss with us in this hour. There's several tricks. One is to pull out something and to make space for the function. And one is to connect the things you know to the thing you don't know in some particular way. There's another trick, but I think I can show that after you learned more topology. That you can prove that at every step there's countable things, just like we have done in the 5th problem. So you do the countable union of countable things that are countable. So you just slice things into countable things. And the usual trick we do is like something 1 over n, like smaller or equal to 1 over n, bigger than n, the usual trick that we use. Any question?